Hi everyone! In today's video, we're going to go over equations that contain polyatomic ions. So a while ago we talked about types of chemical reactions, and one of those types of reactions was a double replacement reaction. Now, a double replacement reaction is also known as a precipitation reaction. So in a precipitation reaction, we have two typically clear liquids that are mixed together and they form a solid as one of the products. So you can see in this picture here we have magnesium chloride to start mixed with sodium phosphate, and they form this white precipitate or white solid product. So how do we know whether something will form a solid? So first, we're going to skip ahead a little bit. We'll talk more about solubility in module 4, but for now, let's just kind of briefly go over some terms to talk about solid products. So first, let's talk about solutes and solvents. So when you have a solution, it's going to consist of a solute and a solvent. So the solute is the minority component of a solution. The solvent is the majority component of a solution, typically water. So basically this is similar to if you have a cup of tea. Let's draw a little cup of tea. And let's say we pour some sugar into that tea. So the sugar is the solute. It's being dissolved in something, and there's less of it than the rest of the solution, which is the solvent. So the solvent is the water or the tea. All right, so typically we dissolve things in water to dilute them. So water is usually our solvent. So then what is this solubility term? So solubility is the maximum amount of solute that dissolves in a specific amount of solvent. So for example, if you've ever had tea with sugar, sometimes there's some sugar crystals left on the bottom of the cup. And usually that's because you've added way too much sugar and it couldn't all dissolve in the amount of tea that's available. So some of it just sinks to the bottom because it can't dissolve. So again, the maximum amount of sugar that can dissolve in a cup of tea would be its solubility. Now, later on, we'll talk about how this depends on temperature, and we'll talk about the units for solubility. All right, so now there is a difference between ions on whether they will dissolve or not in solution. So some ions dissolve really well in solution, and those are called soluble ions. But other ions don't dissolve in water if they're bonded to something else that doesn't dissolve in water. So that would be something called an insoluble ionic compound. So insoluble means does not dissolve. Now, the reason that some ionic compounds don't dissolve well is due to the fact that they are so strongly bonded together. And if something is soluble or can dissolve in water, it's because water can break apart the ionic bonds between two ions. So, for instance, salt, NaCl, remember sodium has a positive charge, chlorine has a negative charge. This dissolves really easily in water. And that's because water itself has some partial charges to it. And we'll talk about this more later, but for now, water has two hydrogens bonded to an oxygen. And there are some partial charges on this molecule. The oxygen side is partially negative, and the hydrogens are partially positive. And water is a great compound because it can break apart certain ionic compounds and kind of wedge itself in between, for instance, sodium and chlorine. However, there are other compounds that water can't break apart. So one example is actually a compound called silver chloride. So silver has a positive charge, chlorine has a negative charge, and water cannot break them apart because they are so strongly bound together. So that would be an insoluble ionic compound. It is so tightly bound, it just cannot be broken apart. So chemists were able to come up with some trends or rules for determining whether an ionic compound can dissolve or not. So these are called solubility rules. So down below, we have a pretty simple chart, table 9.7. Basically, this shows all of the soluble ions, so things that can dissolve in water. So under positive ions, we have lithium, sodium, potassium, rubidium, cesium, and ammonium. So notice that these are all alkali metals in group 1A, except for ammonium, which is a polyatomic ion. And then under negative ions, we have nitrate, acetate, and then we have a few others here, but they have some exceptions to them. Now this chart isn't my favorite chart, so I've also added this chart separately on Canvas. It's a little blurry here, I'm not sure why, so let me actually show you the version on Canvas. All right, so in this table, in the first row, we can see compounds that are always soluble. So those are group 1 metals and the ammonium ion. And then below that we have the nitrate ion and the acetate ion. Those are always soluble no matter what they're bonded to. Then we get into the halogens in group 7A, so chloride, bromide, and iodide. Now these are usually soluble, they can dissolve pretty well, unless they're bonded to silver, mercury, or lead. So remember, we saw the example of sodium chloride, which dissolves really easily, but silver chloride is insoluble. It does not dissolve. So there's some exceptions to the halogens there. Sulfate is generally pretty soluble unless it's bonded to strontium, barium, lead, silver, or calcium. And then in the second box below, we have compounds that are generally insoluble. So if something contains hydroxide or sulfide, generally it won't dissolve in water, unless it's paired with something that always dissolves in water, like the group 1A metals. So this chart, I think, is a little more comprehensive. And I'll always provide this on exams or tests. I don't really expect you to memorize these things. So you'll always have access to this. Let's go back to... So let's look at an example problem. We're going to look at two compounds, magnesium chloride and sodium phosphate. So this is from our, this is kind of similar to the reaction we saw in the first slide. So what we're going to do is figure out what are the products. And looking at the products, which one is a solid or a precipitate? So we're going to use those solubility rules to figure that out. Okay, so because this is a double replacement reaction, remember that the ions are all going to switch places, but in particular, the metal ions are going to switch places. So let's kind of write out all of the ions and their charges. So sodium, we said earlier, is in group 1A and it has a positive charge. Phosphate, PO4, we saw last time, has a 3- charge. And you can always look that up in your table if you need to. Magnesium is in group 2A, so it has a 2+ charge. And chlorine is in group 7A, so it always has a -1 charge. Okay, so if we're switching our metal ions, that means that magnesium and phosphate are now going to pair up together in the products. And then sodium and chlorine are going to pair up in the products. So we're switching everything around. Okay, so let's pair up magnesium 2+ with phosphate 3-. Now remember, we have to balance the charges here. So what would our, or I guess how many magnesium ions do we need to balance the charge on phosphate? So this one's a bit of a trick question, right? Because we kind of need to balance both here. So remember my trick, you can always switch the charges and make them subscripts. So this would be Mg3 PO4 2. Oh, but that looks like we have 42 phosphates, right? So we need to put parentheses around phosphate, or I guess 42 oxygens, which isn't right. Okay, so that's our first product. So what I'll do, oh, I can't erase that, that's right. I had written it previously. Okay, well that's our first product. So we'll label this product 1. Okay, so now let's figure out our other product. So sodium is going to team up with the chloride ion. And what is our formula there? Well, luckily the charge is already balanced, so it's just NaCl. So that's product 2. Okay, so I'm going to rewrite this. Okay, so our products are Mg3PO4 2 plus NaCl. Okay, so now we need to figure out which product, if any, is a solid. All right, so let's go to our solubility rules. Okay, so magnesium phosphate was one of our products. So I don't really see anything about magnesium, but at the very, very bottom of the table, I do see phosphate. Let's see if I can, oh, no, I can't mark this up. Okay. So phosphate is just at the very bottom there. And it says in the green up above that it's generally insoluble unless it's paired with lithium, sodium, potassium, or ammonium. Now in our case, phosphate is paired with magnesium. So that must mean it is insoluble because magnesium is not one of the exceptions. Okay, so this is a solid. What about sodium chloride? Now, I already kind of gave it away earlier, but let's look at our solubility rules. All right, so sodium is in the very first row, and it says that it's generally soluble and there's no exceptions. Okay, so that means sodium always dissolves. And then chlorine is in row 3, or chloride, and that is generally soluble unless it's paired with silver, mercury, or lead. And in this case, it's not. It's paired with sodium, so that would always be soluble. So because it's soluble, we're going to call it aqueous. Okay, so what we're going to do, oh, let me make some room next to NaCl here. So we're going to write in parentheses the states of each of our products. So magnesium phosphate is a solid, and sodium chloride is aqueous because it's always soluble. So what that really means is if we looked at a beaker with this solution in it, we would have magnesium phosphate molecules floating around, and they would just be stuck together there. But then the sodium and chloride ions would be kind of floating around doing their own things because they can dissolve in water. So they can actually separate in water. But magnesium phosphate cannot. Magnesium phosphate's a solid. All right. Oh, there's a random slide with our solubility rules. Okay, so let's now balance our equation, because remember, whenever you have a chemical equation, you have to balance it. All right, so let's make our little chart that we usually make when we're balancing equations. Oops. So we have reactants versus products, and it looks like we have sodium ions, phosphate ions, we have a magnesium ion here, and chloride ions. So notice that I left PO4, the phosphate ion, as one unit. So treat polyatomic ions as one unit. So for instance, we're not going to balance phosphorus atoms separately from oxygen atoms. That's going to be way too difficult. Instead, we're going to treat phosphate as one entity, and we're just going to balance that, and it's going to make it so much easier. All right. Let me just erase these boxes here. Okay, so let's start counting. So how many sodium ions do we have in the reactants? 3. So we've got 3 sodium ions in the reactants. What about the products? We only have 1 in the products. Okay, so how many phosphate ions do we have in the reactants? Just 1. What about in the products? We have 2 phosphate ions in the products. Okay, magnesium ions, it looks like we have 1 in the reactants and 3 in the products. And then for the chloride ions, we have 2 in the reactants and 1 in the products. Okay, so now let's balance. And we're going to balance these ions, or these ionic compounds, using coefficients. So remember, do not change the subscripts. Only coefficients. So the subscripts are how we balance the ionic charges, and then the coefficients are how we balance the molecules and their atoms. So they're different. All right, so let's start with the sodium ions. We need 3 on each side. So I'm going to put a 3 in front of NaCl. So that's going to give me 3 sodium ions in the products. But I'm also multiplying the chloride ions by 3. Okay. So let's balance the phosphate ions. Okay, so I need 2 on each side. So I think what I'm going to do is multiply our first reactant by 2 to give me 2 phosphate ions. Oh, but I'm also multiplying the sodium ions by 2. So now I actually have 6 sodium ions on the left-hand side. Oh, okay, so I'm going to go back to the products. So now I want 6 sodium ions on the product side. Okay. But now I also have 6 chloride ions. All right, so we had to do some adjustments there. That's okay. Now magnesium ions, I need 3 on each side, so I'm going to put a 3 in front of magnesium chloride. So that gives me 3 magnesium ions in the reactants. And I'm also multiplying the chloride ions by 3. So now I have 6 chloride ions in the reactants. All right, so now it looks like everything is balanced. So our coefficients are 2, 3, 1, 6. So not too bad. Remember, if you see a polyatomic ion and you have to balance an equation, treat the polyatomic ion as one unit. Don't separate it into its separate atoms because that's going to make it so much harder. All right. So overall, the steps for determining the equation for a precipitation reaction is to first determine what the products are. So you're going to switch the metal ions around and balance the charges with subscripts. Then second, you're going to determine if any of the products are solids using the solubility rules. Oh, I'm missing a little G there. And then 3, you're going to balance the entire equation and treat the polyatomic ions as one unit. All right. Now, this can be really tricky and it takes a lot of practice to kind of figure these things out. So in your lab report for this week, you're going to get a chance to practice some of these concepts. And I do have a separate video going over another example if you want to watch that as well. And that's listed under the week 5 Panopto recordings. And here are the solution slides for that same problem that we just did. So if you do want to go over that later. And I also have a worksheet on Canvas. It's another balancing equations worksheet, but this time it includes equations with polyatomic ions. And I believe the key is included in that same document as well, so you can check your work as you go. Okay, so that's it for today's video. Next time we're going to talk about molecular compounds, also called covalent compounds. So we've just wrapped up all of the ionic compound information that you need to know. It was a lot of information. And next time we'll talk about the other type of bonding, covalent bonding. So we'll start getting into that. I will see you then.